So today we are going to look at periodic trends and effective nuclear charges and how are physical and chemical properties of elements used to develop the periodic table. So the first thing that we are going to look at today is called Coulomb's law, also known as the inverse square law, that explains the electrostatic attraction and repulsion of elements. You can apply Coulomb's law to magnets, gravitation, and charged particles. We are interested in energy attraction or repulsion between charged particles in atomic structure, ionization energy, and lattice energy. So, Coulomb's law, there are no mathematical calculations used to describe attraction or repulsion between forces, but we will use the following justification when we use Coulomb's law to describe these forces. The larger the charge, the larger the energy of attraction. If opposite charges, or energy of repulsion of like charges. So the bigger the charge, the more energy of attraction or repulsion is there. The smaller the distance between the particles, the larger the energy attraction for opposite charges or repulsion for like charges. So the closer two particles are together, the higher the energy is going to be. So let's use Coulomb's law to compare the energies required to separate negative and positive charges in A and B. So in A, we can see that the distance is relatively close together, so it's going to have a large energy of attraction, but the charges are about equal. When we look at B, we can see that there are two positives and one negative at the same distance as A, so the energy of attraction is going to be larger in B than it is in A because the charges are larger in B than A. I'm going to give you a second to apply Coulomb's law to charges A and C. So we can see that A distance is closer than C's distance, meaning that A is going to have the larger energy of attraction because they are closer together. So let's do one more practice. Let's use Coulomb's law to compare the energy required to separate the negative and charges of pauses in A and D. Which one requires more energy? They both require or have the same amount of energy, but one is attraction and one is repulsion. So A, we can see that they are opposite charges, so they're going to attract, while in D, we can see they are the same charges, so they're going to be repulsed or move away from each other. Now that we've talked about Coulomb's law, let's talk about what shielding electrons are. Shielding electrons are electrons and energy levels between the nucleus and the valence electron. They are called shielding because they shield the valence electrons from the force of attraction or excitation by the positive charges of the nucleus. So let's take a look at sodium. If we look at sodium, sodium has two shielding electrons on the inside of its on the inside between its valence and it. So we can use the knowing of shielding electrons and we can find the effective nuclear charge, or the ENC. Effective nuclear charge is the charge felt by the valence electrons after you have taken into account the number of shielding electrons that surround the nucleus. So if we look at fluorine, fluorine has 9 protons, 9 electrons in a neutral atom. 2 electrons in the first electron shell, meaning that there are 7 electrons in the second electron shell, or the outer shell, meaning it has an effective nuclear charge of 7. The 7 outer electrons experience a lesser effective nuclear charge due to shielding electrons in the inner electrode shell. So we can take the actual nuclear charge, which is 9, minus the shielding by the other electrons to get our effective nuclear charge. So effective nuclear charge depends on both the nuclear charge and the number of shielding electrons. So across the period, effective nuclear charges increase, and down the group, effective nuclear charges decrease. So as we go across the period from left to right, effective nuclear charge is going to increase, and then as we go from down to up, effective nuclear charge is going to decrease. Now, we can also look at atomic radius. Atomic radius is the distance between the nucleus and the outer edge of the electron cloud, and that can have an effect on the ionization energy. And this is the energy needed to remove an electron from a gaseous atom or ion. And then we can also look at the electronegativity, and that is the measurement of an atom's ability to attract an electron. So, atomic radius is the distance between the nucleus and the outer edge of the electron cloud. And the atomic radius can influence the effective nuclear charge and the number of the main energy levels. So the effective core charge, or the effective charge, is an effective The effective core charge is an effective charge determined by subtracting the number of inner shell electrons from the number of protons in the nucleus. So we can see that the atomic radius decreases as we go across the period and increases as we go down the group. So hydrogen has a larger atomic radius than helium does. So down a group, a shells are added and the principal quantum number increases. Valence electrons have more energy and are farther from the nucleus, and the radius increases. When we go left to right, valence electrons are in the same shell, so we're moving and the more protons are added, increasing the force of attraction experienced, thus for decreasing the radius completely. So let's practice ranking the following atoms in order of decreasing radii. So let's look at A together. So I have aluminum, sodium, potassium, and sulfur. Yes, and sulfur. So we know the atomic radius decreases going across the period and increases going down the group. So if I look at aluminum, sodium, potassium, and sulfur, the largest radius is going to be sodium in A, and then I'm going to have aluminum, and then I'm going to have phosphorus, and I'm going to have sulfur. So I'm going to give you a chance to look at the next one, AlGaNNIn, and put those in order from decreasing radius. Exactly. It's going to go from IN, GA to AL because we know that atomic radius increases as we go down the period. Down the group. So another periodic trend that we can look at is ionic radius, and the distance from the nucleus to the outer edge of the electron cloud in a charged ion is going to be our ionic radius. Metals lose electrons and form cations, meaning that the radius decreases. So from potassium to potassium plus an electron, my radius is going to decrease. Nonmetals gain electrons to form anions, meaning that the radius increases. So my calcium plus E1 plus an electron makes a calcium negative, so that radius is going to get bigger. So let's look and rank the following particles in decreasing radii. So if I start and I look at iodine and the negative iodine charge, we know that a cation is going to decrease the radius and an anion is going to increase the radius. So it will be I negative and then I. I'm going to give you a second to do B and C, and then we'll come back and discuss them together. So we know that cations have a smaller radius than just a neutral atom. So I know I'm going to do potassium and then potassium plus. And then if I look at aluminum and aluminum 3 plus, I know that a cation is going to have a smaller radius, even if it's a 3 plus cation. So will be my aluminum and aluminum 3 plus. We can also look at ionization energy. So this is the energy needed to remove an electron from a gaseous atom or an ion. The energy required to remove the first electron, the highest energy electron, is called the first ionization energy. And the energy required to move the second electron is called the second ionization energy. So we know, or we can see, that our ionization energy increases as we go from the bottom of the periodic table up, and as we go across our periods, it also increases. So our lowest ionization energy is going to be francium, and our highest ionization energy is going to be helium, neon, so on and so forth. So let's put the following pairs in order from highest ionization energy to lowest. So magnesium and sodium, we know that ionization energy increases across the period. So sodium is going to have a higher ionization energy than magnesium. I'm going to give you a second to do the last two, and then we'll come back and discuss them. So if we look at oxygen and sulfur, we can see that oxygen is going to have the higher ionization energy because it increases, it is on top of sulfur, and we know that ionization energy increases from the bottom to the top. And then if we look at calcium and barium, calcium is going to be our biggest because it is higher in the period than barium is. So in general, it's generally harder to pull an electron out of a full subshell than it is to pull an electron out of a subshell that contains only that electron, if they're in the same principal level. So if we look at hydrogen and helium, hydrogen only has one electron, helium has two with a full valence electron. It's not going to want to give those electrons up very easily. Hydrogen wants to get rid of that electron so it can be happy not to have it there. We can also see a periodic trend with electronegativity, or the measure of the ability of the atom's ability to attract electrons. And we can see, right, it's going to attract electrons as it goes across the period. So here's a quick summary of the periodic trends, right? We can see ionization energy and electron affinity increase as you go across the periods, while the atomic radius decreases. The atomic radius decreases as you go down the period, but increases electron electron affinity and ionization energy decrease as you go through. Atomic radius increases. So let's get some practice on ionic radiuses here.